Hello dear students, welcome you all. So in this lecture I am going to discuss about the physical quantity entropy. Right. So you might have come across this term many a times while having discussions in thermodynamics or even when you are discussing different branches of physics. Right. So what is entropy? Right. If I answer it in a very simple way, then I can say entropy is the measure of presence of disorder in a system. Disorder in a system. Now, what is this disorder? If someone asks me, what is disorder? This disorder. So, disorder, I'm saying disorder in the system means I'm looking at the system from thermodynamic point of view, right? Let's consider an example. Yeah. Let's look at this picture. We have a picture of two rooms, right? You can see here we have two rooms, room A and room B. Yeah? You can see here this is room A and this is room B. Now you can look at these two pictures, right? Room A is more organized as compared to room B. Clear? All the items in room A are at proper place, right? There is very less disorder or mess in this room. What if we look at the room B, then it is full of mess. Clear? Total disorder is there. So in layman terms, I can say that system A is more ordered and system B is less order. It means system A has less entropy and system B has more entropy. But in actual, right, if I use thermodynamics in all this, right, then the things will get changed. How? Because we don't have to look at the system just from the perspective of its appearance. This is only about the appearance. Here the system looks ordered, it looks disordered, but this is not the way. Clear? When we have make it ordered, we have done the work. We have utilized some energy, right, in doing all this. So then if we do some work, we add energy to the system, right, heat will be generated there, all these things will be done there. So it means entropy will be increased during all that, right? So in total, making all this room organized, total entropy of this system plus the surrounding will be more as compared to this system. But in layman terms, if I simply say that which system is more ordered, which system has more entropy, then obviously B has more entropy as compared to A, because B is more disordered, right? So why this term was required? Now the next question arises, why this term was required in thermodynamics, right? So if we look at the a thermodynamic system, we know, let's take it to their entropy. There. If we look at the system, right, we know the ability of the system to do work is defined by the amount of heat energy present inside the system, heat, Q. Clear? This defines the ability of a particular thermodynamic system to do work. Clear? So now if we have two systems and one system is this one and second system is this one, right, and the entropy of this system is less as compared to this one. Entropy less, more entropy. Clear? Right. It means like this is system A and this is system B. Clear? So if we look at these two systems from the thermodynamic point of view, it means if this system is having more entropy, means this system will have less amount of heat energy that can be converted into work. Or in other words, it can be said that there is this entropy will represent the amount of energy that is not available for doing the work. It can be said in that way. More entropy means less energy for doing the work, or more energy for a not useful as doing the work. This can be said, right? Similarly, in A, entropy is less. It means the energy that can be converted into work is more, but the energy that cannot be converted into work, useless energy, that is low. Clear? So this is how you can make the distinction between these two systems in terms of entropy. Clear? Now, this entropy word was first, coined by Rudolf Clausius. Rudolf Clausius in 1865. He gave this, physical quantity the name entropy. Clear? So, he actually was studying the different thermodynamic systems. Rudolf Clausius, who was a German physicist, he was studying different thermodynamic systems. So, he want to have a physical quantity that measure the ability of the system to do work, right? Or in other way, the ability of the system having randomness. So then after doing several studies, he gave this term entropy. Clear? So now we can say that entropy is defined as the amount of disorderness, right, uncertainty, right, present in a physical system. Or in other word, we can say entropy is defined as the amount of heat energy that is unavailable for doing the work in a system, right? So these two definitions can be used for defining entropy, right? Now I am showing you one more example. Right, you can see here, right? It is clear from here that in the solid state, when the atoms or molecules are very close to each other, obviously the disorder is low, entropy is low. So when we go to the liquid, there becomes spacing between the molecules or atoms. It means they are now far apart. So the disorder is more. So we can say the entropy of this system is more as compared to this system. As we further go to the gas, then obviously the spacing between these molecules increase. It means entropy even becomes more than this, right? So this is the way of differentiating between three systems, right? More order means less entropy, more disorder means more entropy, right? So entropy is a measure of a disorder of a system or energy unavailable to do work, right? So this is the way of understanding entropy. Now I will go to describe entropy in terms of first law of thermodynamics and in term of heat energy, right? So let B have a system. Let's suppose we have a system. This is the system. This is the given system, right? We add somehow heat into this system. Let the heat added is a delta Q, or we can say delta Q, right? This heat is added to the system. Here one thing is very important, that heat is not a state function. Clear? Heat is not an exact differential. That's why we wrote delta. We didn't write dq in all those equations. It depends upon the path followed. Whereas the entropy that we are going to define, it is a state function. Clear? It depends only on the initial and final states of the system. It does not depend upon the path followed. Right? So here we have a system. Let we added small amount of heat, this much of heat into this system, right? In such a way that this entire process remain isothermal. Isothermal means the temperature of the system remain constant. So how it is possible? As we have added some amount of heat energy in the system, but we let the system expand very uniformly, so that the gas molecules or the atoms or molecule present inside this system get a bit expanded. Infinitesimal expansion will be there, so that the temperature of the system remain constant when we added a very small amount of heat in the system, right? So in that case, what will be the first law of thermodynamics? Delta Q is equal to du plus dw. Now du is equal to 0, because we are saying that this system is a isothermal. Clear? This process is isothermal. Temperature of the system is going to remain constant. So I can say delta Q is equal to dW, or I can say delta Q is equal to PdV. Yeah, dW is equal to PdV. Right. Now we know, according to the gas equation for ideal gases, PV is equal to nRT. Clear? So here P becomes RT upon B. Clear? So it becomes, if I put it here, it will become delta Q is equal to nRT upon B dB. Clear? So it will give me this. Now I can take it here. dV upon B is equal to delta Q upon nRT. Clear? So here n is constant, R is constant. So I can say dV upon V is directly proportional to delta Q upon T. What does it mean? What is delta V upon B? Delta V is small increase in the volume, as I said in the beginning, that what we did when we added small amount of it, we let the system expand very slowly, so that there is no change in the internal energy. So due to that, we get a change in the volume. So this fractional change in the volume means fractional increase in the disorder. More volume means more disorder. So increase in this disorder is directly proportional to what? Delta Q upon T. Remember, here I have taken delta Q. I told you why it is, because heat is not a state function. We can't write it dQ. Although in many equations we took it as dQ, but if we go into deep discussion, then we have to restrict ourselves to this symbol, not to D, right? So now it give me this. It means ds, change in entropy. What is dV upon B? Increase in entropy or change in entropy is directly proportional to ds. Not ds. I was wrong. Delta Q it was let it be there. ds is equal to d. Again I am writing d, delta Q upon T. Clear? So it was although proportionality sign here, but I took it as equal to. I take the symbol of proportionality as 1, right? Constant of proportionality as 1. So it give me this equation. ds is equal to dq. What is ds? Change in the entropy of the system. Temperature is a constant. Clear? What is delta Q? Delta Q is the amount of heat either added or subtracted from the system. So obviously, if delta Q is positive, positive means heat is added to the system, then ds is positive. But if delta Q is negative, then ds is negative. So this is how we can calculate the change in entropy of a system, right? Because T is a constant. T is not going to be changed. Right. So if I want to get the total entropy of the system, change in the entropy of the system when the system goes from a initial state to the final state, then I can do it integration ds initial state to final state, that is equal to integration initial state to final state delta Q upon T. So it will give me S final minus S initial, that is equal to integration initial to final, right, delta Q Q upon T. So this is the required relation for the change in entropy. Clear? When a system goes from one position to the final position, right? When there is some addition or subtraction of heat from the system at constant temperature, right? So this is about the definition of the entropy. We have seen that entropy can be defined in two different ways. Either we can say it is the amount of disorder present in the system, or we can say it is linked with the amount of energy that is unavailable for doing the useful work, right? Now, what will be the heat, units and dimensions of this? You can see ds is equal to dq upon T, delta Q upon T. So delta Q means joule per Kelvin. Clear? So the units for this will be joule per Kelvin. You can write it in this way also. So these are the units of entropy. Clear? Similarly, you can write down the dimension formula. Right? Remember one thing, that entropy is a state function. It depends only on the initial and final state of the system. It does not depend upon the path followed. Whereas the heat of the system, heat energy of the system is not a state function. Right? So that's all about it. Oh, thank you very much.